forecasting fire weather in the United States. This actually stems from a presentation that I gave at the AMS Student Conference a couple years ago, I believe, when I talked about pretty much ingredients-based fire weather forecasting. And just as we've talked about ingredients that need to come together for severe thunderstorms and organized severe weather to occur, we also can think about fire weather forecasting in terms of ingredients. And let's talk about those various ingredients pretty much that would potentially support the rapid spread or development of large fires. So rapid spread of fires, development of large fires. Strong winds, effectively to push the flames along. That shouldn't be too surprising. When we have strong winds, can push the fires along. Dry conditions in the lower atmosphere, we're talking about measurements of relative humidity, forecasting relative humidity, pretty much as a proxy for how dry the lower atmosphere is, for instance. Warm and hot temperatures, we're talking about needing that heat present such that ignitions could be supported. If it's dealing with very cold air masses, the potential for ignitions to occur becomes relatively more muted. Finally, the fuels, we're going to use this term, fuels need to be dry. We're talking about the vegetation or the material through which the fire spreads. If the grasses, if the, what we call fuels, biological matter is all wet, moist, green, if we had a major rainfall recently, soils are moist, fuels are moist, and that's going to have a tendency of mitigating the fire weather threat. And so we're looking for dry fuels, vegetation, the material through which the fire spreads, as an ingredient for fire weather. Let's look at a mid-level weather chart. This is a 500 millibar chart from the SPC mesoanalysis that illustrates the type of pattern that we see in the mid-levels that could potentially foster a fire weather episode, in particular across the southern Great Plains. As you can see, a broadly cyclonic flow in the mid-levels, looking at 500 millibars, with a trough over the south central United States. Very intense flow in the mid-levels associated with that disturbance, pretty much in an extensive belt from the western United States all across within that belt towards the northeast United States, extending through the south central U.S. And you can see here, kind of acknowledging that we have a north-south oriented Rocky Mountain range here, that large amount of flow that is has a component orthogonal to the range is going to have a tendency of supporting strong downslope flow over the Great Plains. In particular, air parcels associated with that wind speed maximum aloft are going to quickly descend over the eastern slopes of the Rocky Mountains, extending over the adjacent Great Plains. That's going to be associated with adiabatic warming, drying within the boundary layer on the lee side of the mountains extending over the Great Plains. So having that strong perpendicular flow, perpendicular to the range, the Rocky Mountain front range flow extending out over the lower elevations will have a tendency of supporting downslope winds, warming and drying processes. Now this applies not only to the Rocky Mountains, but any mountains and hills. We can have some of these terrain-induced effects that result in modulations or changes to the boundary layer structure, drying, warming, for instance. So let's look at the corresponding surface map from the mesoanalysis here. As you can see, the manifestation of the very strong mid-level flow across the Rocky Mountains extending over the Great Plains. You can see a tendency for warm, hot conditions extending over the Great Plains, strong winds to the west of a sharpening dry line in this particular case, a surface trough dry line effectively marking the division between that downslope, dry, warm, hot air over western parts of the southern Great Plains, the High Plains region, from relatively more moist conditions in the boundary layer extending northward across eastern sections of the Great Plains and portions of the southeast United States. And so that division, again, with that lee trough dry line feature, will be moist air, dividing moist air from the Gulf of Mexico to the east, from the downslope warming, drying conditions to the west of that boundary, where we have deep vertical mixing and strong winds aloft being manifested at the surface through vertical mixing in support of the potential for fire weather conditions being enhanced. Also, in some cases, when we have strong surface cyclones evolving from a response to the mid-level wave, that can induce a tighter pressure gradient in the low levels that can also enhance the low-level winds as well, combining with these warm to hot conditions, dry boundary layer conditions in support of fire weather threat. Other areas where we also consider the fire weather threat all over the country. I mean, many different portions of the country. All areas can be potentially susceptible to fire weather conditions. There are certain patterns that provide more widespread or common climatological occurrences, as we talked about the southern Great Plains, central Great Plains as well. Other areas include Southern California. I'm going to talk about some of our Santa Ana wind events that can evolve from certain typical patterns. In particular, we have ridging in the mid-levels occur. You can see a 500 millibar chart here. Across the East Pacific, western United States, troughing extending from portions of the central United States southwestward into the southwest U.S. We'll have subsidence between the ridge to the west and the trough to the east. As a result, we'll have, in this type of pattern, the development of a surface anticyclone over portions of the Central Great Basin, as you can see here, with relatively higher pressures over the Central Great Basin. And as a result, the divergent flow around the surface anticyclone over the Central Great Basin will have a tendency of having flow extend outward from that high pressure area toward the portions of Southern California, including the coastal ranges and adjacent foothills. That divergent flow, that mass that extends outward from the surface anticyclone, can have a tendency of experiencing those downslope effects through the coastal ranges and the adjacent foothills toward the coast of Southern California, where we have the winds enhanced, particularly through terrain-favored areas. Local terrain effects, as we talked about in this class, can enhance those winds locally. And we can end up getting those downslope-related warming and drying, increase the fire weather potential. We get really strong Santa Ana winds, sometimes evolve in a pattern that could look similar to this. That could potentially increase the fire weather threat if we have dry enough fuels, warm to hot conditions at the surface, as well as those dry conditions as well. Another phenomenon that we consider in fire weather forecasting are dry thunderstorms. We're talking about the occurrence of thunderstorms where we have lightning occurring, but little in the way of precipitation, in particular less than or equal to a 1/10 inch of accumulated rainfall. Using N-sharp here, you can see a sounding that represents what we would consider to be a dry thunderstorm sounding here. The idea is that with that limited precipitation but presence of lightning, we can potentially have the ignition of fires from the lightning, and then the lack of precipitation is going to be associated with a lack of the fire being put out by otherwise wetting rainfall. So if we had a large amount of precipitation occur, or a wet thunderstorm, that precipitation can have a tendency, accumulated precipitation can have a tendency of putting out the fires. Here, with a dry thunderstorm, we'll have those lightning-induced ignitions potentially occur, and then the fire is not put out by the rain. And so we have to consider the ingredients that come together in terms of supporting dry thunderstorms where we get lightning, but not much in the way of wetting precipitation. So several ingredients here. We have a deep inverted V profile, for instance, as you can see in this sounding over here, with dry surface conditions at the base of the inverted V profile. In this particular case, you can see that that is going to support a large amount of subcloud evaporation. So we're going to have evaporation take place such that we don't accumulate much in the way of precipitation. We'll also have potential strengthened downdrafts through evaporative cooling processes that result in gusty and erratic surface winds, outflow winds that could potentially interact with the fire to spread it out. That can have major implications in terms of affecting fire behavior, as the thunderstorm effectively affects the environment and can locally increase winds through those strong gusty outflow winds. And again, the evaporation here is what can limit the amount of precipitation accumulated in this inverted V profile. Sufficient mid-level moisture present in order to get storms in the first place. That is going to be associated with a sufficient amount of CAPE, a sufficient amount of instability, in order for us to get the presence of charge separation and lightning development in our convection. As well as at least modest storm motions. We need these storms to be moving along fast enough. If a storm were to have these characteristics and stall, we increase the likelihood of wetting precipitation, so they need to be moving fast enough. There has to be some noted storm motion, at least modest storm motion, in order for the accumulation of precipitation to be limited. So these are other elements of fire weather forecasting that we consider. And this is going to be a phenomenon that's going to have a tendency of being favored across the western United States in particular, where we have deep boundary layers evolved during the summertime over our relatively more desert-like conditions in portions of the western U.S., where low-level moisture is limited, where we have a tendency of effectively getting these deep mixing profiles, these deep inverted V structures. But also we can get lightning-induced ignitions even over Florida as well, with copious amounts of lightning occurring with some thunderstorms, and in particular lightning strikes occurring outside of primary rain cores. Those can also start fires as well. All right, a very interesting perspective also in the fire weather realm here is, again, the fuels, the vegetation, the material through which fire spreads. That needs to be sufficiently dry in order for fires to spread and large fires to occur. They need to be dry. Fuel dryness can be influenced by recent precipitation. We consider departures from normal, the presence of drought conditions as well. The green up of vegetation, there is a natural cycle as it warms up, particularly when we have a lot of antecedent precipitation for fuels to become, or for the vegetation to become increasingly green, and that can potentially mitigate the fire weather risk. So really, in many regards, the fire weather forecasting includes a biological component. We're talking about the vegetation's holding of moisture, for instance, and greenness. We need to really consider when assessing fuel dryness. This is an example of a chart, one of many that we would consider in terms of looking at last 30-day percent of normal precipitation to look at departures from normal precipitation that can potentially influence the state of the fuels as well as the fire weather potential. All right, now let's talk about some of the products issued by the Storm Prediction Center in terms of fire weather outlooks. As you can see here, this is examples of day 1 and day 2 fire weather outlooks. This is a specific day 1 fire weather outlook that includes areas of the most volatile fire weather conditions, the most dangerous fire weather conditions highlighted in an extremely critical area. Critical fire weather conditions, as you can see in the surrounding region in red, with the extremely critical in magenta, and then elevated fire weather conditions indicated in orange over here. Local National Weather Service weather forecast offices issue the fire weather watches as well as red flag warnings. Also, for dry thunderstorms, the Storm Prediction Center issues areas of isolated dry thunderstorm as well as scattered dry thunderstorms. Areas, as you can see here in this graphic, indicating where we have some anticipation about coverage of those dry thunderstorms. And again, local weather forecast offices issue fire weather watches and red flag warnings that can correspond to the potential for dry thunderstorms. And then as we look to the extended fire weather outlook covering the days 3 to 8, you can see that we'll issue critical areas when necessary, indicating the higher probabilities, 70% or higher, of the strong winds, lower relative humidity combining with dry fuels and surrounding 40% area, as you can see in this example here. So we have probabilistic delineations that correspond to the potential for critical areas where we have 70% as a threshold for a critical fire weather area. And then somewhat analogously, but with the corresponding different probabilities, we'll have critical areas for dry thunderstorms that correspond to 40% probabilities for dry thunderstorms here, in this case with a surrounding 10% dry thunderstorm area for this particular example as well. So again, a review of the ingredients for fire weather forecasting we consider for the development of large fires, for substantial fire spread, strong winds, low relative humidity indicating dry conditions, warm or hot temperatures, as well as the presence of dry fuels, vegetation, or effectively the material through which the fires can spread.